thanks for joining us. It's going to be exciting to share with you the scaling search infrastructure topic. Basically, we have been working a lot over the past few months and years, actually, on the next generation of our infrastructure with a redesigned engine, and we are going to give you a preview of that. It's not fully ready yet, but it's going to be soon. So we wanted to give a sneak peek to people joining us today. First, a little bit about myself. My name is Julien. I'm a product manager today at Algolia on the search infrastructure. My background is as a software engineer. I did full stack development for a few years, then joined Algolia as a solutions architect. So I was working on optimizations, on support for customers, basically implementation projects, and helping on anything really Algolia related, but more especially on the technical aspect. And I switched over to product management to bring that knowledge and that experience with customers and on the engine to try to build the future of the engine. So let's dive right in. What we're going to cover today. First, a quick history of the engine, like how it was built, how we arrived where we are today. Quickly go over the current architecture, what it is, how it works, and then why we had to plan and design a new architecture and how we did it, what are the core concepts, and then a quick FAQ to answer directly some frequent questions. But actually, if you have questions during the talk, feel free to send them in the chat. Betty, you can help me answer them.
Yeah, of
cool.
course.
Yeah, so let me know if there are some questions because I cannot see them. And then, we can either do it interactively during the call, during the talk, sorry, or keep them for the end. Both work perfectly. All right. So first, a quick history of the engine. The engine that we have today was designed 10 years ago. It's a long time, and at the time there were some core principles that were used to build it and to design it. The main ones were to optimize for speed and relevance. So Algolia has been built in C++ for the best performances. It's a custom engine, fully custom with custom algorithms, custom data structures. And so the goal was really to make consumer search the best possible in terms of the quality of the results, but the speed also of the experience. Algolia has been designed as well to provide exceptional reliability, availability. We wanted to have a platform that developers can trust and that can scale and sustain high loads without having any downtimes or any performance issues. So that was really built into the infrastructure as well and the core architecture. And finally, to make that possible, instead of using the cloud that at the time was already big but didn't offer the type of optimizations and the advanced machine configurations that we have today, so Algolia designed custom bare metal machines and built what you could call a private cloud, which is today very large. And we'll cover that in a few moments. So the combination of those three core principles really guided how the engine was built, designed, and grew over time over the past 10 years. And yeah, today that's the engine we know, that is fast, that is relevant, that offers a lot of features. And we are trying to keep all those great benefits and principles to go to the next level for the new one. So let's look a little bit more into the details on what it is today. So Betty, I'm sorry, the designs are very ugly.
What is happening here?
Yeah, so this is a technical project, so we are more focused on the code than on the design. So yes, that's what we came up with. At least, hopefully, it's understandable. So yeah, when you use the Algolia API behind the scenes, you have the main component, the main unit that is a cluster. Any Algolia application, so any environment of any customer, is always going to be hosted on one cluster. It can be a dedicated one, but also a shared one. But the principle is the same. It will be a cluster of 3 machines today. And so what you can see here is that when you send an update, so that's what we call jobs here. So when you want to update your indices, so send objects to be searchable, basically, the cluster will receive them and the machines will synchronize between them to agree on the sequence to index and to make sure everyone has all the data so that each machine can have the exact same copy of the indices in the end. And then on the search side, since each machine has its own dedicated indices, we can use only one machine to search. And so searches are going directly straight to one machine of the cluster. The core principles of that is that you have first quite a lot of capacity because you have not one, but 3 servers. And it's extremely reliable because we never put the 3 machines of the cluster in the same data center, meaning that if one data center had a failure, if one machine had a failure, you always have 1 or 2 available to search. So this is one way Algolia makes the reliability, the availability really high. It's by having this principle of the 3 clusters that are always identical and could sustain a search load. And then you can see on the side that we have DSNs. It stands for Distributed Search Network, and that's Algolia's mechanism to add machines either to increase the search capacity or to distribute globally in the whole world the search engine and make it close to the user so that the latency is the smallest possible and the results are as fast as possible. So these are the core principles of today's infrastructure, this cluster of 3 machines with potential additional DSNs. And it provides, again, speed, reliability, and those machines are what we call bare metal. And so, yes, here what I want to show you are some numbers of what we can sustain today. At the cluster level, so on one cluster, what we observe today is we have indices of up to 500 gigabytes. We can sustain query spikes of 10,000 requests per second, actually more than that, during events like Black Friday, like flash sales, or special events sometimes where our customers advertise something on TV and then everybody rushes to the website and starts searching at the exact same moment. And then some numbers on like what we observe as well is 150 plus millions of searches per day for some customers. Literally every single day we have that kind of volumes, and more than 200 millions of updates sent to a single cluster per day. So it can be all the stock updates, all the likes and changes that end users might make to the data that are reflected in Algolia, amounting to a total of more than 200 millions.
Yeesh.
Yeah.
That's a lot.
Did you know that actually, Veli?
No, I'm really shocked.
Yeah, and that's just a small part of the infrastructure.
Goodness,
So
now I can't wait for the improvements.
that's the challenge. And so globally, what we have is this distributed infrastructure that is in 17 different regions, 70 different data centers. So that's how we achieve this reliability with servers that are never all in the same region. And the total volume, the latest estimation we have of the total volume we get during a year is 1.5 trillion searches. It's hard for me to quantify and understand what this number means, but if we do the math, it means that basically at any given second of a year, we have about 50,000 queries on our infrastructure. So that's a lot. It means really every second that passes, we have 50,000 queries that are handled by the infrastructure. So that's a lot, and that's already nice. But what we're going to see, and if I'm going back to that diagram we saw before, is that if you want to scale that further and you want to address larger use cases, you want to be able to sustain even higher loads, this will be limited at some point and in some ways. And the main way it is limited today is that we have to have everything contained on one single machine, as you can see. Each machine is identical, which is nice for reliability, redundancy, but it's a challenge to make it scale because then we can only scale vertically, having bigger machines. And that's not always possible to find bigger machines because machines cannot grow infinitely. So at some point, we would need to scale horizontally and be able to not have all the indices on one machine, and to also not have the builder and the searcher that are competing for resources. Because today, that's what's happening, is that the same machine is doing both building the indices, so ingesting the updates, and also searching at the same time. And so there might be a competition. So when you want to scale, there's a lot of questions. We need to anticipate and put the right amount of machines ahead of time. And that works well, but it's just not the most optimized and streamlined, let's say. So how do we take these core principles? We take all the nice things about the current architecture, and we just make it evolve towards something that can scale virtually infinitely, let's say. So this is what we do. You can see with the color coding that we are trying to keep the same, concepts. So we had builder green, searcher blue, and storage red, and you keep the same colors here. So basically, we are breaking up the engine in smaller subsystems, in separate subsystems, independent. And so what we do here, as you can see, is that we can have any number of machines just for indexing. So they would receive the indexing updates, and they can build in parallel and have more or less machines depending on the needs. Same for the search. You can have different searching units, as we call them, and then scale this up and down depending on the needs. And this would scale and absorb a larger load, basically. So, and in the middle, you have the index storage, which is the kind of the glue, and it's the way we connect both. And by making these subsystems independent and basically not tied to one machine anymore, what we're doing is that we are making it completely auto-scalable and with a perfect basically adjustment of the needs. If you need much more indexing, we can sustain that. If you need much more search, we can do that. If it's not at the same time, it's fine, because we can scale up and down independently. And the storage is cloud storage, so it's virtually infinite. And by the way, speaking of cloud, that's a core principle as well. We are moving to a cloud-first architecture, meaning that we will not be on bare metal anymore, which we have to manage and scale, but we will be able to leverage the cloud to be a bit more flexible and be able to add and remove capacity dynamically to make this scale. Is it clear so far? Are there questions in the chat? No questions?
Not at this time, but if you have any questions so far, please feel free to pop them down in the chat, and I'm happy to read them out to Julien.
Yeah, and actually I went a bit fast over the previous architecture. So if that wasn't clear, or if there were some questions about some choices maybe already, feel free to shout. It's welcome. So that's the principles of the new architecture. And here we're really looking at how we can sustain more load, with keeping the same principles we had and applying it to a new design that basically breaks up the subparts. But then how do you scale the data size? That's another challenge. Here we're saying, okay, we can absorb more, but how do we have bigger indices, basically? And to do that, today Algolia is optimized for roughly 100 gigabyte indices. We can go further because we have custom machines that accommodate for more, but it doesn't scale infinitely. So if you go above 100 gigs, we need to find a way to make it scale and ideally make it scale across machines to not be tied to that one machine capacity anymore. And the way we do that is we use a very well-known mechanism in the industry, which is called sharding. So if we imagine a big 400 gigabyte index, we would split it, for example, it's just an example, in 4 different shards of 100 gigs each. And this way we could potentially treat each shard as an independent index. And so you could imagine tomorrow, if the index keeps growing and reaches 500 gigs, 600 gigs or more, we just need to add more shards. So we would reshard dynamically and keep growing and keep like those small chunks of an index that are smaller than the whole index, and so easier to work with, faster to work with. Obviously, there's a ton then of extra logic to make this multi-sharding work, but we will cover that in a second. Still no question at this point?
No questions so far yet.
Perfect. So if we tie it all up together, we get this final diagram, which is, as you can see compared to before, where all the jobs, so the updates and the searches were going to the same place, the same cluster. Here, what we have is that each type of operation is going to a different subsystem. So it's going to be different machines in the end, in the background. And here, what we have introduced as well is that the builders can be on different machines and can have different shards. So a shard can be just one index, one full index. But if the index is really big and we want to shard it, then we can have different builders taking care of the different shards. Then when the builder implemented, like processed the updates, it will send the updated indices to the storage, and it will notify the search subsystem that it needs to retrieve those updated index to reflect that in the search results. And so it's the same principle on the search side, where you have the searchers that can be on different machines, potentially on the same machine as well. It's very flexible, and have either several indices or just one index, or even one shard and a subpart of an index. And so on top of those units that are building and searching, we have new layers, new services that are handling the routing of the operations, obviously. But at the same time, if you start to have shards, you need to have a logic on top of it that rebuilds the logic of only one index for the end user. So on the search side, what will do this is the reducer, which will basically gather the results from the different subparts of the index, the reducer in the middle, and it will compute the final list of results for that whole virtual index that is composed of those different shards. And then there's an autoscaler part as well that will monitor how the searchers are loaded. And if they are overloaded, then it will add more searchers for the specific indices that are queried particularly more. And when the load goes down, it can remove the extra capacity. And so it really follows the usage and really scales up and down along with the needs. So that's really nice and something that is quite new. That's it for the final visualization of what it looks like. A few more slides to maybe provide some insights into the project itself. So just for this new architecture, a few numbers. It's been going on for a bit less than 2 years. So it's a long project, a very ambitious project. And we have over 3,000 commits on the code base, more than 2,000 reviewed pull requests. So it's a lot of work, with the unit tests and with each one reviewed by a human. It's not like automated reviews. So that's a lot. I don't know if you have 2,000 pull requests on the repositories you work on, Betty?
Well, the closest one was for Magento, so
it was big.
That was pretty
big. Yeah, we have several big projects actually, like this one at Algolia. And so 90% of that repository is Go. And I mentioned in the beginning of the presentation that the engine has been built in C++ for performance reasons. And so you might wonder, did we rewrite everything in Go? And absolutely not. We kept the engine in C++ for building and searching and all those critical parts that need the best performances. And the Go language in that project is used for the skeleton on the cloud that manages the fact that now everything is distributed. So we took everything from one machine, distributed it, and we had to glue it all together with additional state management, with additional network logic, and this is all done in Go. And it's such a big project that we had over 30 contributors internally at Algolia working on the project. And if you're wondering, okay, does it mean that everybody working on the classic engine stopped to work on that? Definitely not. It's a new team, or we could say a mixed team. But those numbers, you would have roughly the same on the classic engine. So we keep, the same investment on the classic engine. We keep having the same amount of updates. And yes, it's a big project. A quick FAQ to finish. So is it going to be a different product or API? Not at all. It would be transparent for you to go from one to the other. It's the same features, the same API. everything works the same. What about backwards compatibility? So a very small amount of things might be different, but actually we strive to keep everything as identical as possible. So all features should work the same, and you should expect the same. Is it the first time that Algolia's engine will run on the cloud? Actually, no. The custom configurations with big machines I mentioned that we are using since a few years are already running on the cloud, but it's the first time it will be cloud first. So it's still a different step in terms of architecture. What cloud providers will be supported? It's all built to be cloud agnostic. So the goal for us is to support at least the big three, Google, Amazon, and Azure. But ultimately, we could potentially add more in the future if there's a need. Will it be open to all customers? Yes, definitely. And how can customers migrate? It's something we are working on. We are building migration tools to do it completely seamlessly and transparently. But another way could be to have just the two in parallel, and you reindex your data like you would maybe on a regular basis, just to the new infrastructure, and then you change the front end that could point to the new application, and that would be it. It's not yet available, but it's going to be very soon. So yeah, if you have more questions about it, let me know. Thank you very much for joining and for being here. And if you have more questions or want to reach out, you can at firstname.lastname@algolia.com. So Julien.Paroche@algolia.com.
Yeah. We do have a couple questions in the chat. So definitely, hopefully Reed and Tashim will be able to reach out and talk to you. I would also, maybe we can answer one of the questions, is how do we stand out from Elasticsearch? It's a common question that we get here from Algolia, right?
Yeah, definitely. Elasticsearch is really a big competitor. It's also a really mature and complex software. And our goal is not really to be exactly like Elastic or to compete directly with them. Elastic is really a big toolbox that can be configured and optimized in many ways. Algolia's approach is to try to provide a lot of the same capabilities, but not all the same, but to make it a little bit easier to start with and to have to worry less about the hosting part, the configuration part, managing add-ons, and how to integrate different features together. We try to package things a little bit more to have everything hosted on the infrastructure so that you get started quickly. You don't have to worry about scaling, and that's the purpose of that project. And so, yes, it's a slightly different philosophy, but it's definitely Elastic is a very great tool, actually. And yeah, we'll keep improving.
Yeah. And I think it's time for our next host. So we're going to take a 2-minute break to get him technically set up. Thank you, Julien, for your time.
Thanks to you for your help. Thanks, everyone.
I would love to see the results of that the next DevCon when it's all
we'll probably have customers in production, so it will be nice to do a retro.
All right, we'll come back in the next DevCon 2023, and we'll hopefully know more about these improvements.
Right. Perfect.
We'll be right back.
Thanks so much. Bye-bye.